Okay, so I was just looking at a YouTube video that I made about the model, um, which I use some tables to represent the model, and I get into exploration of prime numbers and things. And I realized it's pretty confusing, so I wanted to just step back and explain where it comes from. The first thing I did was to do a table of the Fibonacci numbers. I made it along a one axis. It works pretty good. The one axis um, just allowed me to use division to relate the Fibonacci numbers, and lo and behold, this other I can't remember what this is called, but it's something that has to do with like Fibonacci number study. It's a different set of numbers, but it's the same progression, and this is what you get coming down this axis, and so it's all fairly straightforward. You can see how it's developed. That each of these columns is so you can see that the denominators remain the same, and the numerator changes, um, but it meets up at this um, one axis where you have the identity. And I made um, I thought since I had this beautiful representation of these numbers and it works so well that I would try and do this with the integers and see what would come of it. But when I entered into the integers table, it wasn't just with kind of a continuation on from the experiment I did with the Fibonacci numbers and making that table. That caused me to realize things um, um, about maybe prime number theory and stuff that I'd been thinking about, and also a way to put that stuff together and think about it and try and work with it. And also, I have been doing, I have this prospecting device, uses these rods that cross. Believe me, they cross on their own. I'm not making them do it. I know people say that even it could be a sympathetic thing I'm not aware of, but no, guess what? I really don't think so. Anyway, um, uh, I made the different little models of the furniture, like the Ark of the Covenant and then the Ark of Incense and stuff that would have been in the temple or even the tabernacle, actually, even predating the temple. Um, and then I put that device on the model of the ark, and I tuned it I painted it all with this gold paint, and I tuned the 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 device to the frequency of the paint, and I was able to get some pretty interesting concentric circles going out from it that I needed to explain. And this seemed like a way that I might be able to approach explaining that too, in some kind of combination with prime numbers. So I made this table of the integers, which this is just one of a basic, one of many. This is one I can show you that's not too badly scrambled up with notes and different things that are on it. Um, and so it has the same one axis because you have identity with the numerators and denominators. How you have the denominators in each column are the same, and they progress after they will have met here to be the identity. Um, so you get something really interesting with 0, for instance, um, which is actually, I think, very important. You get also like the 2 uh, axis here, the 0 axis, um, uh, and things like that that are worth noticing. And yes, I also made one with just primes, so there's no non-primes in there except for one, but that's it. So you can have the one axis, but then it's all working for you the same. Um, well, you'll notice a little bit different of the boundaries of this table um, because it's only made of primes. Not to be outdone, I also made a table that is made up of only the non-primes. Okay, before we go too much further, I just wanted to say that the order that I present these things in is kind of important. Uh, I need to explain something about that is with these tables. You can do certain operations, and the operations that you perform uh, seem to reveal something about the topology that exists for those tables. Uh, I want to introduce the idea of topology, but not get into the specifics of how it all plays out and stuff, because I just want people to think about shape and stuff like that, that these kinds of things might ultimately come to if we're talking about dimensionality, which, when you get into these tables, you realize that they do produce some sort of dimensionality, and you can see that when I talk about integrating these tables, the thing that comes out from 0 and has the one axis is just going in that single direction in recognition of the one axis. But it's possible to imagine this thing as a three-dimensional uh, a sphere, if you will, the integers table, which I contend that the primes table is actually a torus, and then you have the really interesting shape that takes place with what you then have with the table that's made of all the non-primes, and because you have a lot of randomness in there and stuff that comes out with like, for instance, if you went back and you froze it, you followed the, the 2 column down normally at that nice angle. Well, it doesn't do that. It's really pretty. It's kind of dog-legged and stuff, and so there's a different shape that is. Okay, so I'm getting into this so that I can tell you that the operations do produce, without talking about the operations, I'm getting into this to tell you that the operations do produce this area in the integers table, where the prime numbers are represented by um, the results of the operations that are done somewhere else. But then you see that you have these columns where, see the red here, um, where in these specific columns there is spacing. This is an operation which I did to reveal the why there might be the concentric circles in um, the area going out from the arc model that I had my little prospecting device on. This was what I did, those operations that brought this about, that revealed what could be responsible for concentric circles, the presence of where the primes are located um, in these columns. So I'm going to back out here. Okay, so when it's backed out here, you can see that you have the same representation. And what happens is um, this space, it's ever larger with each column that drops down, um, so that it takes up more area, and expands, and you don't get a lot of expansion over the top. You usually have, as far as I've seen, only two um, numbers which are represented above the one axis, but then you have an increasing number below the one axis that increases with each prime that you discover, and then um, it expands in this certain way so that it fills this space in the integers table. And this space that is filled is the space that we now next want to consider when we compare the integers table to the primes table. Okay, here we go. I wanted to try and move my image, but somehow or other my program's not letting me. So I'll try and explain this to you, how it goes along. I have on the top here of a split image the integers table, and down here underneath, this is the primes table. We are looking to assess whether we could find the next prime number. And I'm contending that if you do this calculation and you say that the result must be less than 1, when it equals 1, it's not yet right. So when you have 6 over 2, that equals 3, and we've been doing this basic operation, which I haven't talked about, but I can reveal some of yet, which is division, and so it's got to do with this divided by that. So it would be, if this was 3 divided by 3, you have this angle, 3 divided by 3 would be 1. It has to be, the result needs to be less than 1. So we know we have to go on to the next number, which is 7. And this is how we find 7. But you will discover as we go along, seeking these next numbers, 11 and 13, that the equivalent of 1 that we're looking for changes due to the expansion of the table. But you will see that the equivalent of 1 actually appears in the integers table and helps us as we go along looking for the next primes. Okay, so now that we're looking for the next number, the number 11, you can look at all my notes here because this really helps. And it becomes self-evident by looking at what I have written here, what I'm talking about. So if it was 10 over 3, it wouldn't be good enough because we're looking for 0.6, right? We know this because 1 divided by 1.666 is 0.6, isn't it? And that's our point. And that appears in the column that does not have to be defined by the number 11. If we don't know that it exists, this column is for something that's just much further back. So we don't even know that 11 exists when we come up with this number. So the point is not something that relies on us for the first time, actually, in looking for this sort of thing. We're not having to face that sort of challenge. Everything is reserved in numbers which are already revealed to us as we look for these other numbers which are larger. So that's pretty cool. We're not thwarted by what has almost always thwarted us before, even if we get to a very long and complex chain of events and we find at the very end that it's not supported because we needed something that was already at our number or larger. Um, that doesn't happen here. And so you see, with finding 13, the same situation goes on. Up here, you have the point, 0.75 in this case. So if it were, we're trying to find the next number, we assume all of this rest of this prime numbers table doesn't even exist. We don't know what the primes are. We're trying to find the next prime. We found 11, so we're looking for the next prime. Let's try 12. That's the very next number. 12 divided by 3. Um, it doesn't work because that equals 0.75. If we use that and plug that in here, 3 divided by 4 is 0.75. And that's our point. We see that up here in this column. And interestingly, it's presented to us. And so in the comparison of the tables and in the column that we might expect it to be in. So we have to go with 13 because that result will be less than 1, well, less than the equivalent of 1, which is 0.75. And there is logic to this as it develops. I want to admit, though, it doesn't hold up. I mean, once expansion gets going and keeps going in these tables, um, uh, eventually you lose and you don't see those numbers up there anymore. You have to begin to do some math, and they're parsed between and things like that. But I just found this to be really interesting, and I thought that people who do this sort of thing and look up how prime numbers are formed could really benefit from looking at this because it's so cool. Just to say, it doesn't give up right away. I mean, it holds up for a while. That you have this proving out of how you can discover what the next prime number is, and there's your equivalent of 1.625. When you try 16, that's what it comes to in the calculation, and it doesn't work, so you have to do 17, and that's how you find 17. It's got to be less than 0.625 when you do the calculation, so very interesting. And it keeps doing that for a while, and you know, I just this is very much about how I think that um, um, actually the universe is made of math, and that it refers to itself in the same way that I use division in these tables, which means I'd like to share with you some more. I didn't make enough comparison images. But it keeps going for a while, and I'd like to tell you where it breaks down and different things like that, but I can't because it was such a long time ago and I lost heart, and I kind of don't remember a lot of this stuff. You know, I've had to kind of refamiliarize myself to do this explanation, and which is why I'm not getting into the basic operations, if you want to be honest, because I just really wanted to explain um, some of the more overarching things which are important about this. You know, the philosophical type stuff and how I think what it means. to look at the whole construct, and how topology can come into these tables, um, uh, and create what I think are, with the integers table, something like the proton; with the primes table, something like the electron; and with the non-primes table, something like the neutron. And we're dealing with math to explain the universe. There's a different sort of association when you're talking about fusion and what goes on in the nucleus and what the atom's even made of, and that it's not particles or waves, but it's something quite else. It's math, and it's math, and it's math, and it's math. And maybe um, I can help you understand what I mean. So I'll just pop these things up here for a moment so that you can get a better understanding. Um, yeah, this is, it's called the projective plane, or it's, you understand it like with Mobius strips, you know. Um, that's what I would think of as the neutron, and this would be the proton, and this would be the electron. So what I'm talking about when I'm talking about the model, the arc model that I came up with, it's based on where I put the prospecting device on the arc model, and I tuned it to the frequency of the paint, and I got the concentric circles. So I have this model for space-time that expands outwardly at the prime number shells, which were where the electron would be involved. And then you have the reason for it is something like the neutron being present in that space-time that's created by um, the proton. Just the neutron being present there, and something about it, and it creates. See, there's a different idea of fusion there. That you don't get two protons, but you have this same central um, mathematical idea of zero that these things progress out of, but that you capture when you do fusion, you create a new neutron that gets captured, and then it also produces because of that basic thing, you have a excite or a realization, if you want to say it like that, at the next electron shell, that's possible to exist going outwardly. Um, uh, so it's different like that. Um, but it doesn't buck. Nothing about this bucks anything that's ever been proven in physics. It's just that, hey, wait a second here. There's a different mathematical way to explain everything that's ever been arrived at. It's a different model, and it's valid. This thing works. Believe you me, and it explains everything about reality coming from the atom, but it doesn't explain the atom in terms of quantum physics. Instead, it explains the atom in terms of this sort of math and how these neutrons develop when fusion takes place, and you have new different levels of reality um, with the electrons at the various shells going then outwardly in the space-time that is developed by the integers table. And so you have this appreciation of that. And I might add, um, there's something about particle physics that says, oh, well, we collide these things um, in a particle accelerator, and we get these results in these collectors, and that proves that it must be particles. And I'm telling you, it does not prove that there must be particles, because I've done some experiments with my prospecting device when I've had the arc model set up, and I can tell you that you can generate new centers of interest, if you will, or centers of being in the space out there that's generated by um, the arc being excited to the field, and you can create another new thing. And I'm telling you, if the field that's generated, say, by the proton, by the zero over zero sort of generation of it with the integers, that in creating that sphere, and the expansion of space-time that's appreciated along the one axis, as you've seen, that it represents expansion of space-time out there. If we can integrate that into a sphere, and it creates for us an atom that we have when you get another neutron, and they fill in, and then you have these, that it's just like nature, because you have a certain appreciation here, right? Where because you can see that every single time you have these collisions, you're always going to have, like, this math means that you get the discovery of prime numbers right, but only out to a certain point, right? And so it's just like isotopes in nature. That's what I'm saying, is that isotopes even prove this might be the way the atoms are developed, because you can even have um, uh, false discovery of primes that happens out there beyond a certain point, and it's possible, and it should happen, actually, and you should expect it, and you should have isotopes, and it should be like this, and it should see it. It matches what you ought to see in nature. So I'm just going to end with the recording I did of the experiment that I think presents a challenge to particle physics, because it says that the results that they get in their collectors could be coming from a different sort of thing than what they have always interpreted the collisions and the particle detections to mean in terms of the nature of the atom.
So now I'm going to use the arc model setup to demonstrate how you get a different sort of signal. I'm going to set something up over here, somewhat in this area, where we get a signal. This is, remember, we're out here, we're all unlocked. We get inside this triangle and we're locked. We get unlocked coming out of it. We know from our previous, it's kind of a triangle, and then there's a connection here between the incense altar and the arc, and we know that close around the arc is a bit of a thing too. So what we're going to do is we're going to go in here. We know we get a more or less permanent signal in here. We'll just charge up something in here, like for, say, something on the order of 25 seconds or so to keep this video short. And we come out here and release it. Now we have an unlock. And then what we can do is we can step on the same spot and our rods will lock. We're looking for just after the 12, if you can see the second hand. good day for the unlocking thing. But then what we can do is we can also do the same thing again here. Get another, say, something long enough to really be able to determine that it is a time added, not just 5 seconds or 10 seconds. We'll add another, say, 20 seconds here, holding this. I can see, although you probably can't, where my feet were, so I know where I was standing. So I stand here again, and then when I release it, and I come off, and I go to get on the same spot again, I started just after the 12. So what we're looking for here is to show that in this setup where the generator is generating on the arc model and not from the edge of the electron shells, like it's being used when we're conducting normal prospecting. When it's set up this way, according to this model, which corresponds to our mathematical model. Okay, there we go. Here's your 5 plus 20 plus, or minus however much, and they unlock. So what we got to do is show you that it's not connected by a signal from there to where the generator is. There's nothing round about this that's causing it to have a connection. It's more field. Actually, that works in our favor because it's telling us where they can determine in this model.